Question number 19 that has been made from Doppler effect, and a nice story has been added there with the submarine case. The first speed is 5 meter per second, that of submarine A. Submarine B would be moving with 7.5 meter per second. And it says that submarine B is chasing submarine A. And A has a speed of 5 meter per second, that has been said there. B has 7.5, and the speed of sound is also there, which is 1500 meter per second. Now B sends a sonar signal of frequency 500 Hz that is reflected from A, and eventually we need to calculate what would be the frequency received by B after reflection. That is the main purpose to be calculated. Okay, Doppler's effect, and two steps we need to apply. The first thing, let me calculate the apparent frequency received by A. That will be the real frequency, and speed of sound, let me denote it by V. So see, A is the detector, so that's going to be V minus of VA downstairs V minus of VB. That is all used with respect to the sign convention in the Doppler. A is the detector, B is the source. After that, now let's see, if I put F2, that's the frequency which is received by B. Now this B acts as detector, A acts as source. I'll be getting F2 is F1, which is the source frequency, multiplied by V is the speed of sound, and here is the detector coming towards this. So that's V plus VB, and source is there, so that will be having V plus VA, because this time the source is moving away. So downstairs that has to be plus. Okay, now all you need to do is that put this value of F1 there, and F2 is what you need to calculate, the frequency received by B after reflection. Do that. A bit of calculation is required. Yes, I agree on that point. But then you would be reaching to option number 4 as the correct one. Now let's move to the 20th question. The 20th question is in fact a nice combination, though if you have practiced a bit higher level question, this should not be a trouble. And there is a concave mirror down and water, and there is a particle. The depth is given there, which is 5 centimeter. So what does it say? The concave mirror has a radius of curvature 40 centimeter. In fact, I don't require that radius. I'll be requiring the focal length. And it is filled till a depth of 5 centimeter. A small particle is floating on the surface of water, and we need to calculate its image as seen from directly above. That means you have been given the paraxial vision. Okay, see now what is the step? First, that would get reflected. Initially no refraction. It would get reflected and then refraction. Let's go. Now first of all, I would like to calculate the image formed by the mirror. 1 by V plus 1 by U, and U would be minus 5, would be equals to 1 by F, and that's minus 1 by 20. So let's see how much will that be. That will be 1 by 5 minus of 1 by 20, and that is 3 by 20. That means the image formed by the concave mirror is at a distance 20 by 3 down, plus it's a virtual image, and that's true because the object distance is less than the focal length. Now when that light gets reflected, it appears to come from the distance, and that distance is 20 by 3. So what would be the object distance for the refraction? That will be 20 by 3 plus of 5. Now for the second situation, for this given case, the object distance, let me call it as U dash, would be 20 by 3 plus of 5, and that comes out to be 35 by 3, all right? So object distance is 35 by 3. And then a refraction. So ray going from denser to rarer, that will be 35 by 3 divided by mu, which is 4 by 3. So effectively, the image distance would be 35 by 4, and that would be 8.8 centimeter. So option number 4 is the correct one for this question. Question number 21. The 21st question is here. To verify Ohm's law, a student connects the voltmeter, and that voltmeter is connected across a cell having a certain EMF and internal resistance. There's an ammeter. And on the basis of this thing, say a graph of reading of voltmeter versus I has been plotted. And it says that V0, the final one, is almost equals to 0. That means when the current is 1000 milliampere, in that case, the reading of the voltmeter is almost equals to 0. On the basis of this data, we need to calculate the EMF and the internal resistance. Okay? So together with that, we also need to calculate the resistance supplied, and if that comes out to be correct, we are going to certainly tick upon that. Let's see, the first thing is, what you need to do is, if you see the graph very properly, at 0 current, the potential difference is 1.5 volt. And that now can be said, when current is 0, this potential drop is 0, so the entire reading of voltmeter will be EMF. So one thing is clear, the EMF of the battery is 1.5 volt. That has been done. After that, one more thing. Let's just focus here. When the current is 1000 milliampere, the potential difference across the battery is 0. So when the current is there, you just see, when you calculate the net potential difference, that will be EMF minus potential difference of the resistance. The two potential difference would be subtracted to give the terminal PD, and that terminal PD is the reading of the voltmeter. Now, that comes out to be 0 when the current is 1000 milliampere, the terminal PD. That means at 1000 milliampere, this potential difference is exactly equal to 1.5 volt. So 1.5 volt will be 1000 milliampere, of course, is 1 ampere, multiplied by the internal resistance, which is R. And that gives me 1.5 ohm. So on the basis of this, you see the EMF and the internal resistance has been calculated, and luckily the first option immediately comes out to be the correct, and since it's a single option, so I need not go and find the other options. Option number 1 is the correct option for this question. All right, let's move to the next one.